you very much for coming along to listen to me this afternoon. I really appreciate it. And I have no idea how long this talk's going to take, but it won't be several hours, so don't worry. It'll probably be about 40-45 minutes, and but I'm not sure because I've not given this talk yet before. But I'm just trying to, in this little presentation, give you a summary of what we've done over the years, and it also gives you an idea how research programs grow and evolve, and sometimes you end up doing things that you didn't expect that you would be doing when you first started the project. And this is a story actually of a very happy collaboration over several years now, and I certainly hope it will continue into the future. Okay, so I thought I'd start off letting you know where I come from. And where I come from is that I am a foraminiferal specialist. And these are beautiful scanning electron micrographs of benthic foraminifera from the Sunder Shelf, done by my master's student, Sam Martin, who was here 2 years ago. And he's still working on his master's thesis, and he put this slide together especially for me, which was very kind of him. But what I'm talking about today is adapting to a changing world, and because that's what we all have to do, because we're all probably very familiar about climate change and sea level change. These are things that are happening to us right now. It's not really happening to our children, it's happening to us. And we absolutely have to adapt to these changes. Some of these changes, yes, we may be causing them, but some of them may well be natural. It's sometimes very, very difficult to tease apart what are the natural changes and what are the anthropogenic changes, but changes are taking place no matter what. And it's interesting, when I talk to the trustees of the university that I'm at, they say, oh, I don't believe in climate change. And I'll say, why not? And they say, well, I just don't believe in it. For me, that's not a good argument. And I basically tell them that what we probably all know is that from the day, the minute, the instant our planet was formed, its climate has changed. That's the only constant to our planet is change. And that's happened every year for the past 4.6 billion years, and it will continue into the future. In fact, it would be very, very weird if things didn't change. And so we're going to talk here about adapting to a changing world. And I want to acknowledge several people here. I can't acknowledge everybody. It's too many names. I wrote down the names in my little book during this visit who've helped me just on this visit, and it fills 2 pages. But I just wanted to point out a couple of people here, and you can see their names who've helped. And I really, truly appreciate that, because this is a collaboration. We couldn't have done it without all these people helping. And particular thanks to Prof. Lockman, Prof. Noor, and Prof. Vijayan for supporting the collaborations that we have between our 3 institutions. Okay, so this is what, 2 slides ahead, Noor, this is when it started. Okay, UMT and ECU signed an MOU in 2006. And it was an MOU between high-level administrators, so it was basically very, very general, saying that let's collaborate in research and academics in general. And then a delegation from ECU came here in 2007, probably around about 10 people, and I was part of that delegation. And I was wearing a suit back then because I was the interim director of an institute, and so I had to wear a suit. But I haven't done since because it's hot here, and so I don't intend to wear a suit here again. And then there was a return delegation to ECU the following year, and Noor came along, and we were able to reciprocate the very nice field trips that I went to go on when I visited here. So I took Noor out on Pamlico Sound out on a boat trip. Pamlico Sound is a little bit smoother than the oceans around here. Point that out to the people who were on the Discovery with us a few days ago, which is a very interesting feeling, certainly for me anyway. I don't know about you guys. And, but we started our research collaboration here afterwards, led by Noor and myself in 2009. And I came over here with a couple of colleagues, and we spent a lot of time working in the Setu wetlands. And I'm going to show you some pictures of this. And then, as Noor pointed out, our research has branched out, and we're now working in the South China Sea. And since this research began, we've sampled every year. That's what we did again this year, and we've published papers with co-authors from both institutions. And this started 7 years ago, and already we've published 6 papers, which is pretty good. Basically, it takes a year to get something out. And so we've done one a year since then, and which is pretty good because we're all busy doing other things. So I think it's a very good rate. And there are co-authors listed here from UMT and co-authors from ECU, and I will point out an awful lot of the work at ECU is done by our graduate students, and so yes, we owe them a debt of gratitude, but they're involved in our publications, and on several of them they're actually the senior authors. So here we have 6 papers published so far, 3 more currently being written with graduate students as senior authors. These are the 6 articles so far. I don't expect you to read all of that, but I just wanted to point out that they're in pretty good peer-reviewed journals. This last one is probably the highest impact factor out of these 6, and the next paper will likely be published in 2017, so we'll have a year's gap, and then we'll have a few more coming through after that. And the theme of our collaboration is adapting to a changing world. Not adaptating to a changing world, but adapting to a changing world. And I was just telling my graduate student down here that if you ever spell a word wrong on a PowerPoint projection, I'll really have a go at you. And so, of course, I've done it here twice in my first 4 slides. So this is what you don't do, okay? So that's the theme, adapting to a changing world, both natural and anthropogenic, and there's a very simple scientific question here. And the scientific question is, what environmental changes have occurred in the recent past, and what might these mean for the future? And by the recent past, we started off thinking maybe the last 10,000 years, but as we'll see, I think I'll mention in this talk, we actually are finding some records which go quite a lot farther back than that. And the research so far, because little work has been done on the foraminifera in this region, there are students here in the audience who are doing this, but there's not been that much in the past. Most of it has been on mangrove swamps, and there haven't been too many of those. And so first of all, what we have to do is collect baseline data. And then when we get those baseline data, we can then use those data to interpret something in the past. So we've collected baseline data from from the estuary lagoon, the mangrove swamps, and then once we've got those baseline data, we can do something a little bit more sophisticated, try and reconstruct sea level rise. And then we looked at the effects of fish farming, so in other words, you're looking at anthropogenic change in this case. And then we went offshore a couple of years ago, and we're now collecting baseline data offshore. And we're going to use that baseline data to make these interpretations of paleo-environmental change in the past, including these sorts of paleoclimatic changes if at all possible. And we have a variety of tools that we use. I'm the foram guy, so this is the only bit I do. Other people do all of these other things, so it's a very large team of people, and they're students. We obviously study the forams, because that's what I do. We study the sedimentology, bulk sediment magnetic susceptibility, elemental analysis, oxygen carbon isotopic analysis, and then various dating techniques. For very young things, we use lead-210 dating, data back about 120 years. Then we'll go to radiocarbon dating, get back about 40,000 years. And then to go even farther back, hundreds of thousands of years, we use optically stimulated luminescence dating. And just to let you know, in the work we've done so far, we only have, I think, 4 OSL dates, and the reason for that is they cost $1,000 for each date, and it takes a year to get each date. And so it's a huge investment, and so you spend a lot of time figuring out, should I or shouldn't I? And that's probably the way we're going to have to go in the future to date some of the sediments that we found, for example, on this trip and the last one. Then we've also done some ground penetrating radars, I'll show you in a second, and some side scan sonar information. So it's a multi-proxy approach. It's very complex to try and put it together. When you have one line of attack, it's very, very easy to make an interpretation. But when you do something like this, it gets harder every time you add a new layer. But that's what science is about. It's not supposed to be easy. Okay, so foraminifera. So I'm going to show you a few pictures of forams because that's what I do. And just to show you how small they are, this is a needle. This is the eye of a needle, and there's one foram sitting there in the eye of the needle. There it is blown up. This is the aperture through which it extends its pseudopodia, because these are like an amoeba with a curly shell, a single-celled animal-like protists. This is the aperture blown up, and right there's a black arrow pointing there. And what's there? Another microfossil. This is a calcareous nanofossil. This is essentially planktonic algae, which are so tiny that when they die, they break up into their component plates like this, and you can see how tiny they are compared to this. And then these break up even more into the component plates, and when you get thousands upon millions of these, you end up with a rock called chalk. So the White Cliffs of Dover are essentially made out of the tests of billions upon billions of these little microfossils. This is a live foram on a look under a light microscope. So here's the foram test or shell. Here's the aperture. You can see the pseudopods sticking out. And so in comparison to an amoeba, which have lobose lobopods, these are very fine, and these are called philopods, and they use these to move or to catch their prey, as we'll see in a second. Here's a planktonic foram. Here's a diver collecting one just by swimming a couple of feet down in the ocean and looking upwards at the sun, and you can see the foraminifera floating in the ocean, and you just simply get a jar and screw the top on, and you collected a live planktonic foram. And here's a live planktonic foram. Pseudopods are arrayed along some spines, and here he's catching a copepod. And they can be quite aggressive, and these spines actually bend, and the cytoplasm essentially envelops the copepod and goes inside the copepod and dissolves them from the inside out. It's an awful way to go, and thank goodness that foraminifera are tiny. But they may be tiny, but they're incredibly abundant. The rocks that form the pyramids are made almost 100% out of the tests of foraminifera. So that's how abundant they can be. And remember now, these are just a few of the blocks of limestone that they mined, quarried, to make the pyramids. So they've been very abundant throughout approximately the last 450 million years of Earth history. The reason why so many people study foraminifera, this is actually an oil rig off the coast of Kuala and Terengganu. The reason why is they're very, very useful for finding oil and gas, because you can use them to date rocks, and you can use them for paleoenvironmental interpretations. And so if you add up all the micropaleontologists in the world today, you get a number. And that number is all of the other paleontologists added together. The dinosaur specialists, the brachiopods, the mollusks, the clams, the brachiopods. Add all the paleontologists up, there are less of them than there are of micropaleontologists. It's because they're so useful for finding oil and gas. Okay, so what you do is you basically collect a sample of sand or mud, you break it down, maybe in water, soak it overnight, stir it a little bit, and then you get a little dampened paintbrush, look down the microscope at the sand that's left, and here's the sand on a picking tray, a bit out of focus, but every single one of those is not a foram. It's a sand grain, and you have to pick out the forams from among the sand grains. And then you put them on a slide. And so here's a slide prepared over many hours just for one sample. So if you're doing a project with several hundred samples, it takes 3 years. You know, so this is not very easy work. It's not actually intellectually challenging picking the forams, but it is relaxing. I used to hate picking forams when I was a student, but now I have students. And so I don't pick quite so many. And this is all very low tech, but I just wanted to show you we do some higher tech things. This is an image student Sam Martin did last summer. It's a CT scan of a foram, so this is actually, oops, excuse me. This is the, sorry, I've done it again, there you go. This is the scan of the chambers inside the foraminifera, and these are the little connections that join the cytoplasm together. And this next one is a 3D printed model of a foram from the South China Sea. Okay, so how do we work with forams? This is the basic slide. Those of you who've got a geological background have probably heard about the present is the key to the past. In other words, what we learn about the present, we can apply to the past. And so what we do is simply go to a modern coastal environment. Here's the ocean here, here's the land, and we look at all of these modern environments, from the deepest ocean to the shallowest, hardly any salinity at all, 1 part per thousand you might get forams. As soon as it's freshwater you won't get them. And we look at all of the different environments, and they're all listed here, as you can see. And in every one of these environments, there'll be a different set of foraminifera. There might be some species found in several environments, but every one of these environments will have something that is restricted to them. So we have that knowledge, that's the baseline data. We study the distribution of modern foraminifera, and then we use that information to interpret samples in the subsurface, the pre-recent samples. And so this is the sort of approach that we took. We went to the Sekitaran wetland, and you all know where it is, so I'll move through this slide quickly. These are the questions that we were looking at in the Sekitaran wetland. First of all, we're getting baseline data, and then we were going to use those baseline data, the stuff I just showed on the 2 slides ago, what forams are found where. Then we're going to see if you can use that to investigate pollution in the past, and also you can investigate sea level change. And then an awful lot of surveying took place, and some guys may have been involved with that. And I really appreciate Nazir in particular led the charge on that one. And we're trying to understand the response of the coastal system to Holocene sea level change. And this is basically what we do. We collect a bunch of mud, just look at the top centimetre, because I'm only interested in the foraminifera that live in the top centimetre, because that's where most of them live. Some can live deeper, but I'm really only interested in the top centimetre. Here's an expert grab sampler right here, that's Joseph. And we took samples all the way along the Sekitaran wetland lagoon. This is where the inlet was in 2009. Okay, and so what we find is that this is the freshwater rivers coming in here, so there's a salinity gradient all the way down here, very low salinity until it gets to about there, then it gets higher near the inlet. It's high here near the fish farms, and then you go farther north, it drops off again. And these are scan electron micrographs of the majority of the most common foraminifera from the Sekitaran lagoon. And here's that salinity gradient I was talking about. So down here, this is not 2, this is 0.2. 0.3, 0.7, and then we get 1, 2, 5, 2, and then it jumps up 18, 29, a bit of variety here, and then it gets to about 30, 32 at the inlet, and then it drops off again in this direction. But you see by the fish farms, it's quite high salinity, because this area is bathed in the waters that come in through the inlet, and it basically, I'm getting ahead of myself here, but it helps clean out all the organic matter of the fish farms. Then it drops off up here. So this is the salinity gradient 7 years ago, and I'm going to return to this at the end of the talk. And this is the results of the foram study, where we simply got all the abundance data of foraminifera at each location, identified them, did a cluster analysis of the data, and we recognize, we recognize 4 major groups. There are different species characterized in each group. So in other words, this is exactly the same as I was saying earlier on. You document the distribution of the modern day foraminifera, use that as the key to the past. And we can relate this distribution of these 4 assemblages very nicely to salinity. You can see this is the low salinity, mixed salinity, high salinity, mixed salinity, going off towards low salinity again. And here's a plot, just don't worry about temperature at the bottom. Here's the low salinity one, biofasces A, slightly low, slightly higher salinity, high salinity, salinity dropping off, and then this is the north of the lagoon. So this is from southeast to northwest. So there's a great correlation between salinity and the foraminiferal distribution, which is no real surprise, but you do have to demonstrate it so you can use the information from these assemblages moving on. So we not only worked in the lagoon, we also worked in the mangroves. So in particular at 4 sites where we wanted to find the baseline data on the distribution of mangroves foraminifera along 3 transects, and then we caught, this is me here trying not to breathe water as I'm collecting a sample in the Sekitaran lagoon at the beginning of the mangroves. And then we did an awful lot of surveying because we're trying to relate the foraminiferal assemblages in the mangrove swamp to elevation. And if we can relate them to elevation, then if we find fossil mangrove foraminifera down core, we can make an attempt to reconstruct sea level change. And that's what we'll get to in a second. So an awful lot of surveying took place, which is not that easy when you're in the middle of the mangrove swamp. And then we took cores using something called a Russian corer. You have a large version here, I think you call it a D corer. And you push this into the ground, and maybe in this environment, because it gets very sandy, this is quite a sandy mangrove compared to the other coastal Malaysia, and so you can get in around about 3 meters tops. So you go through the mangrove peat into the underlying sediment, and we didn't know the environment that underlying sediment represented, but by having studied the modern day distribution of foraminifera, we can then interpret the environment in the underlying quartz sediment. And lo and behold, it proves to be estuarine sediment. So in other words, that is the substrate that the mangrove plants basically started to grow on to form the mangrove environment. And these are the mangrove foraminifera. There's about 24 really common species here. There are a few rarer ones as well. So you've only got about 30 species to deal with, so it's not that many. This is a core, from the top of the core down 80 centimeters, and you can see what we're doing here is lead-210 dating the cores, and the cores are not all the same. There's an awful lot of variety in sediment accumulation rate, from 18 millimeters a year down to 1.7 millimeters a year. So this is probably some sediment dumped down quickly, either by a storm or some other activity in the swamp. And then what we do is relate the distribution of the foraminifera to elevation. And this little diagram here, which I know it's out of focus, but let me just walk you through it. This is the low tide mark. This is intertidal down here. This is the low tide mark. This is low tide. This is the the low marsh or low mangrove. This is the high marsh or high mangrove. And then you go into fresh water. And this is the distribution of species along that transect. So different species live at different places along that transect, and you relate that to elevation, and you can then use that to interpret these cores up here. Okay? And so what we find is that when we radiocarbon dated a sample at the bottom of one of these peat cores, that the oldest mangrove peat that we have here in the Sekitaran is only about 300 years old. And we've been able to reconstruct sea level rise since then. And so this is a sea level curve. This is 10,000 years ago here, 10,000, 9,000, 8,000, all the way to the present day. This is related to sea level. So this is minus 25 meters. There's sea level right there, that's plus 5. So here's the sea level curve. Coming up the data from different types of data from 10,000 years ago, the sea level curve sea level rose quickly here. Then around about 7,000 to 5,000 years ago, there was a sea level high stand, which is about 3 to 5 meters higher than it is today. And it's dropped off. And this is the age, and that blue dot there represents the peat that we dated at the bottom of that mangrove swamp core at about 300 years. And using the foraminifera, what we're able to reconstruct, so this is now today, the year 2020, so that's into the future. This is 2000, this is going back in time, 1950 is right there, that's when I was born, somewhere back there. Going back to 1820,
Okay, so the peak went back to 300 years, down here somewhere. So sea level's been rising at around about 1.6 millimeters a year until around about the turn of the century, the 20th century. And then within the space of about a decade, the rate of sea level rise tripled from about, well, doubled, excuse me, from around about 1.6 to 3.2 millimeters a year. And interestingly, we did a similar study in North Carolina, and in exactly that same decade, the rate of sea level rise tripled there from 1 millimeter a year to 3 millimeters a year. So this is clearly a global signal, and so tide gauges in this country also show this sort of pattern. So after several thousand years of sea level fall, 300 years ago, sea levels started to rise. And that's what we here in Malaysia have got to deal with in the future. There we go, there's the summary statement. Okay, so the highlights of this sea level study right here is the Setu wetland deposits contain a good record of recent relative sea level change. It's much harder to work in the mangroves than it is on a salt marsh in North Carolina because they're nowhere near, they're very irregular in elevation, they're nowhere near as smooth, but it is possible. Sea level change is identified using forams in the different types of dating, and after 4,000 years of generally falling, sea level began to rise, and the rate doubled. And this study was the first time, to our knowledge anyway, that early 20th century increase in rates of sea level rise have been demonstrated at low latitudes. Okay, so moving on, the next stage. This is ground penetrating radar antenna, and my colleague Dave Mallinson, when looking at the Google Earth map of image of this part of the world, was very intrigued by the pattern he saw. And so he came over here and brought this with him and ran transects across these ridges, 3 transects, and where there are yellow dots, that's where he took optically stimulated luminescence samples. And what do you see? Well, let's point this out. See that yellow, point it out again. See that yellow road there? This is now an oblique view, and these are all the little dots here are the palm oil pines. And this is the cross section that we see along that transect, and we see all these reflectors in the ground penetrating radar dipping in this direction towards the sea. So these are ridges that built out towards the sea as new amounts of sand were built out. And this is where we took an OSL age. Okay, this is this same image blown up. And basically you can recognize different patterns in this data. You can recognize the different sorts of patterns. You can give them names, you can describe them, and then you can interpret the environment that they represent. So this one is a washover, this one there's a lower shore face. Different ways you can interpret these, and you can understand exactly what environment these sand bodies were deposited in. And I keep doing that, sorry. And this is how we collected these sand samples. And basically you dig a trench, you take a sample in there, you don't let the light get to it, and you wrap it up and take it home and hope that customs don't insist on seeing inside it, because that would ruin the sample. And then you get some dates, and here are the dates along these transects. Unit 1, which is farthest inland, proved to be about 6,000 years old. Unit 2, stretching down here, was bracketed by this age, and so represents between 3 and 2,000 years ago. Unit 3, 1.9 to 1.4 thousand years ago. Unit 2, what's that? 1.4 to only 300 years ago, which is exactly the oldest age we have of the mangrove swamp, which is this Unit 5 here, the last 300 years. So you can see an evolutionary history of the coastline here. And so, in other words, this is where the coastline was about 6,000 years ago, which is no surprise because that's at the high stand of the sea level, and so sea level extended farther inland than it is today. And since that time, the coastline has been building outwards. Okay? But now, and that's during a period of sea level fall, but now sea level is rising. And so the coastline is going to start marching back in that direction. And what will happen through natural activity is that this barrier island will break down. And guess what happened during the last monsoon? Right where the fish cages were, the barrier island broke down. Unfortunately here, your barrier island is broken down right outside of INOS, but that's in large part because of anthropogenic change. And so you've got anthropogenic change causing that, but you have natural sea level rise on top of that, which is going to make it worse for you guys. So I'm going to make sure I visit INOS in the next 10 years, because 10 years from now, I'm not too sure. Okay, so here's that same sea level curve, and now these red dots are the OSL dates plotted on the sea level curve. They plot on it very nicely. Don't bother reading about this. But bottom line is we can understand the coastal evolution through these combination of different approaches. Okay, now moving on again. What's the effect of these fish farms? Well, we've got all the baseline data for the foraminiferal distribution here, so what is the distribution of the foraminifera, and what's the abundance, what's the diversity, right there at the fish farms? Because I know they're clearing a lot of the mangroves to put in other sorts of aquaculture, but you can't keep putting more and more in. There has to be a limit. So we were interested in trying to see what that was. And again, we chose several locations. Two locations up here near the main fish farms, and another one down here in the estuary where there used to be a fish farm, but it is now not being used anymore. And so here you can see the sample sites adjacent to all of those fish farm cages. And I won't belabor the point, but let me just show you this one core. This is a core down at this site here where no longer is fish farming taking place. And we date the cores through lead-210 dating. We find out from talking to the local people of when the fish farm started and when this fish farm stopped. And this is the percentage of sand, right here, about 80% sand before the fish farm was put in. This line is when the fish farm was put in, and look how rapidly you drop down to almost zero sand and all you get is mud. And at the same time, the amount of carbon skyrockets. And so what you have here is orange sand overlain by black mud, overlain by orange sand again. So the environment got back to the normal conditions very, very quickly once the fish farming stopped. And the other thing I'll note is that the fish farms which are located up in this part of the river, they're flushed daily by the salt water coming in through that inlet. Now unfortunately that inlet is now closed because there was another anthropogenic change a couple of years ago and a new inlet was opened here. And by opening this inlet here, it helped cause that one to close. And so it makes you wonder now about the future for the flushing in those fish farms. So, you know, human beings have a long history of doing something for a particular reason and it affects something else. And this might well be one of those circumstances. And so the summary of the fish farm study at that time when we did it was that basically we documented the foraminifera, the amount of organic matter at the fish farms. There's no clear evidence at that time of negative impact on foraminiferal communities because of this, certainly in the normal marine area, because of all the flushing. You could say that there were negative effects down in the estuarine area in that fish farm that closed down, but perhaps that was the reason why it closed down. It says there, the final point, the current intensity of floating fish game farming in the Institut lagoon appears to be sustainable. Well, yes, then, 2 years ago we did this study, or 3 years ago, but now the inlet's closed. And so that makes you wonder what the future's going to be. Okay, finally, and then I'll end. This is what we're up to now. We're working offshore, and we start off by collecting baseline data. So 2 years ago, my students and I came across here and we collected surface samples along transects. And the reason why we did this is because the year before I collected some cores. And I had a student work on the cores and we realized we just really couldn't interpret them as well as we'd like to because there wasn't any baseline data. The only other study, extensive study on benthic foraminiferal distribution on the Sunder Shelf, it was done by some Germans and their collaborators along the North Sunder River, which is a river isn't there anymore. It's on the Sunder Shelf, but it's off the coast of Sarawak. So nothing on this side of the world. A gentleman called Biswas around about in the 1960s published on a couple of samples, but nothing really on a consistent basis. And of course, students here at UMT are now adding to the database of benthic foraminiferal distributions, which complements the work we've got here. Or maybe I should turn it the other way around. This is complementing the work that's being done here at UMT. And so these are the pictures that Sam Martin took of these are beautiful pictures, because he not only takes SEM pictures, he takes light microscope pictures as well, which he automatically, the camera takes them at multiple focal depths and then automatically builds them together and makes a very nice image. And what do we see? Well, you can't see the different symbols there because of the focus, but basically you have 5 different biofasces, assemblages, a near shore one there, and another one off there. And so the assemblages change with depth. And so if I have a core from the subsurface and I collect samples along that core, I'll be able to recognize changes with depth down that core. And that's one of the several of the projects that my students are working on. And Rokia, is Rokia here? She's also working on core material. And so this work that Sam Martin does here will help Rokia interpret her cores. And Sam was here 2 years ago and left. Was it 2 years ago, 1 year ago? 1 year ago. 2 years ago. And left some pictures so that people here could help interpret their microfossils. Okay, so this is now the current research that we've got going on right now, including during this trip. And I love coming here because this is such an absolutely beautiful part of the world. I show this picture when I go home and everybody wishes they could come on my trips. This is how I recruit graduate students. I show this picture. And then what we do, this is on the Discovery 2. We collect gravity cores from the back of the ship. So this is a gravity core. It's got a 2 meter or a 3 meter barrel. We have on 2 occasions filled a 3 meter barrel, but for some unknown reason it's very difficult to get more than 2 meters. But believe it or not, with a 2 or 3 meter core, you can cover the entire Holocene, 10,000 years. On most of the Sunder Shelf, Holocene sediments are only 1 meter deep. And so we select as the target area for coring paleo valleys that were cut in the Sunder Shelf during the last ice age when sea level was 120 meters lower than it is today. And the reason why we select those paleo valleys is because they are still low spots on the shelf today, so it gives you more accommodation space for sediment to accumulate. And so we predict that we will find more than 1 meter of Holocene sediment in these paleo valleys, and lo and behold we find 2-3 meters. And I'll get back to that in a second. So here we are lowering the gravity core off the back of the ship. And here's an example of the core that comes up. This is probably a 2 meter core tube full of sediment. And this is just to show you that it isn't quite as easy as it says, because you can see there, that's a ship. And so you're sampling whilst the boat's rocking, and but realize this weighs about 3/4 of a ton, so it's not an easy thing to do, and you have to be very, very careful. And this time we went out on the Discovery, and it's much easier to deploy and bring in the gravity core. And then you process in the lab, cut the cores in half, get someone who's good with a saw to do that. And this is what the cores look like. This is disturbed material at the top of the core, because obviously if you drop essentially a large heavy dart into the seabed, it's going to blow away maybe 10-15 centimeters of surface sediment. Then you bring it out, it's probably going to disturb some of the surface sediment. And so we scrape the core carefully to find out where it's in situ. And in this case, this was disturbed down to about, well, these little scratch marks here. This is where we're taking 1 centimeter samples. So we take 1 centimeter samples all the way down for 2 to 3 meters. So this time we collected 4 cores. So you can do the math. That's a lot of samples that we have to look at. And here we are cutting up cores last year. It's a miserable job. She's only smiling because the camera's pointing at her. And we had 2 teams going, cutting up cores on 2 tables. We did a similar thing again this year. Okay, so let's look at the sea level curve again to finish off. When I showed you the last sea level curve, it was organized in a different direction. This is now 21,000 years ago, and this is today. So 120,000 years ago, sorry, that's not right, excuse me, let me get this right. 21,000 years ago, sea level was 120 meters lower than it is today. All of that water was taken up in the ice sheets. And so the Sunda shelf was dry land. You could walk to Sarawak. Okay? And there were rivers, large rivers flowing across the Sunda shelf. And there are papers been published which suggest that it wasn't heavily forested. It was heavily forested around the margins, but down the center of the Sunda shelf it was far enough away from sea that it might have been savanna vegetation. Okay, so this is around about 20,000 years ago. And you've got to realize that the fossils of hominins that have been found on the various islands between Sumatra and Java, they date to around 18,000 years ago. And so you can imagine our ancestors, maybe our species, or maybe even Homo erectus or Homo floresiensis, walking across the Sunda shelf at that time. It's absolutely possible. Now, to actually go from island to island, there's deep water between many of those islands, and so they would have to have had boats. You know, and then the first humans had already got to Australia around about 50, 60,000 years ago. So this is quite late on in terms of human migrations. And so, but you can imagine humans walking across the Sunda shelf 20,000 years ago. Okay, and this is what it looked like. So this is the coastline, around 120 meters lower than it is today, and these are the major rivers that were flowing across the Sunda shelf. This one is the North Sunda River. This is the transect along which the German scientists I told you about did their survey. This is the Paleo Chao Phraya, is that the right pronunciation? Paleo Chao Phraya River. And if you look at the size of that drainage basin, that's the size of the Ganges or the Indus. So these are massive, this is a massive river, probably with just as much water as the Ganges and the Indus today. And this flowed across here, incising, cutting down, incising a valley, which has since been filled with sediment. We know that because a paper was published just 2 years ago by a couple of petroleum geologists, I think one of their students. And they ran geophysics across here and showed it was filled, this Paleo Valley, it was recognizable in the geophysics record, and it's filled with sediment. And they said that the top layer in the geophysics that was represented was probably Holocene. And you know our Holocene is 2 meters thick at the most. Their Holocene was supposedly 16 meters thick because it's filling in a much larger valley. And so what we were doing this summer, last week, was basically we took the boat out. Oh, sorry. We took the boat out from here. This is diagrammatic. This is real. This valley's there. This is diagrammatic because there's no geophysics there, and the Terengganu River would have come off here as a tributary. So the last few years we've been coring in the tributary of the Terengganu River, which is a tributary of this much larger river, and getting 2 meter long cores. But here there should be 16 meters of Holocene, and so this time we were out there coring in this Holocene sediment. And the trouble is our coring device can only take 3 meters maximum. And so if it truly is 16 meters thick, then our cores that we took this year should only be about 2,000 years old. And the rest of it still waits to be cored. Because the oil companies would have cored through this when they drill for oil, but they throw it all away. They're not interested in this. So I don't blame them for that. They're interested in finding oil. But they throw it all away. And they also drill shallower wells, not wells actually, cores, when they try and determine where they want to site their rigs. And so what we're interested in doing is getting from Petronas the cores that they drill when they trying to figure out, should I put the oil rig there, or does it have a better substrate to put it here? Those sorts of questions. And of course what they do is they take these, they have a company, a consultant company takes these cores for them, they log them and say, oh, it's sand, they throw them away. To us, they're absolute gold, and they're being thrown away all the time, which is very, very sad. I mean, it's amazing scientific information that's being thrown away. Okay, so let's show you what some of these cores look like. I can't show you what the cores along here look like, because we only just took them this summer, but I can show you what the cores along the Terengganu River look like, and here they are. This is really out of focus down here, but this is Kuala Terengganu here. This is land, this is the ocean. There's bends in the contours there that show you that this is a tributary, right here, river, and this is a valley. We took cores along the valley. So here's the cores now arranged from onshore to offshore. And at the bottom of the core is mangrove swamp sediment, with mangrove pollen. Dates 12,000 years old. So this is just before sea level got high enough to flood it. Mangrove swamps again, but there's marine sediment on top. And I can't read that, and I know you can't read that, but this is around about 5,000 years old, this is about 1,000 years old. One of these cores, this one here, goes from 9,000 years to 1,500 years. That's almost the entire Holocene. Overlying the mangrove swamp sediment is sort of a transitional unit, which you can see here, which is rich in organic matter. Foraminifera occur immediately you get into saline waters, so there's no foraminifera in here, because mangrove swamp forams don't preserve very, very well, they fall apart. The calcareous forams come in here, benthic forams, all the way here, all the way up here, all the way to the top. So here's this blown up, these two cores blown up. So this is the area which is transitional. We have benthic foraminiferous from here all the way to the top, benthic foraminifera from there all the way to the top. Planktonic foraminifera only start there and there in that core, which is interesting because the only place you find planktonic foraminifera now, today, based on Sam Martin's work, is once you get to water 50 meters deep. So that tells you that this water here was probably around about 20, 30, 40 meters deep, and that's when it finally got deep enough for planktonic foraminifera to be preserved in large enough numbers that we're going to find them. So you can see a deepening of water through this core. And final thing, just to show you how complex it is, trying to interpret this, you look at this core and you say, look, it looks just like this core. You look at this curve, which is percent planktonics, it looks just the same. The sedimentology looks just the same. There's even a shell layer in the same place. But when you do the radiocarbon ages, this is now the data from this core up here. This is 200 centimeters, so that's right down there. When you do the radiocarbon ages, this is 9,000, and this is about 1,500. On this core, this is about, if I remember rightly, about 5,000 down here, and about 4,000 there. So an incredibly fast rate of sedimentation. So it means that this core, even though it looks just like this one, this core only represents this period of time right here. And this core here has all this interesting changes that take place after that aren't represented in this core at all, even though they're only about 10 kilometers apart. Every core is different, and that's what we weren't expecting that. It's very complex trying to put the story together. And just to finish off, I keep saying that, this honestly is the end. This, I'd forgotten I had this in here. This is another collaboration we have with JMG and UMT in paleo valleys of Bintulu, Sarawak. So here's Bintulu. This is a paleo valley right here. Here's another one here. There's another paleo valley there. And these were all cut at the same time when sea level was much, much lower. We have cores which were taken around about a decade ago, and we've sampled them. And without getting into all the details here, you can see that we have very nice changes of climatic data up core in these cores. And interestingly, the patterns that these two cores, because that's all we've got right now. Patterns that they show over here are somewhat different than the ones we have over here. So there may be a difference in climatic change on both sides of the Sunda Shelf. Exactly what might be the reason for that, I'm not going to hazard a guess at this point because we're still putting together the data. Okay, this is what we did this trip. This is where we went and cored off KT, right there, and this is the valley of the Paleo Chao Phraya River, which is recognised, so we cored right over the top of it. Then we cored off the mouth of the Kuala and Terengganu River right here because we wanted to study the distribution of foraminifera to see how they're affected by the sediment and fresh water coming out of the river, and the fact that longshore drift in one season is that way and the other season is that way, which is quite an unusual thing, so we wanted to see the effect of that. And then we also sampled in the Setu Lagoon because I want to see what the effect is on the foraminiferal assemblages of the opening and closing of all these inlets that are changing through time, and what effect is that going to have on the foraminifera. Okay, so this year, what did we do? Well, we signed a new MOU between UMT and ECU, and this is a more specific MOU that we signed this year, specifically to further research and academic endeavours in the area of coastal and marine science in the southern and south China Sea and environs. We had a general MOU, now we have a more specific one saying we're going to concentrate on things like paleoclimate change, which I understand is an emphasis area for UMT. So I think you can see from what I've described to you here that the UMT-ECU coastal collaboration is alive and well. Long may it continue into the future. And thank you very much. So end with a picture of 4 amps.